Look up at the night sky, and you'll see a seemingly peaceful expanse dotted with stars. But the truth is far more violent. Our planet has been scarred by countless cosmic collisions, each leaving behind a silent witness, an impact crater. These massive scars tell stories of chaos, destruction, and rebirth. But what if some of these craters are hiding something even more extraordinary? What if, beneath their familiar shapes, lie secrets buried so deep that they could rewrite our understanding of Earth's history? Imagine a crater within a crater, a hidden impact zone concealed for millions of years. This isn't science fiction. It's a real phenomenon that scientists are just beginning to uncover. Take the Chicxulub crater, the infamous site linked to the extinction of the dinosaurs. What if it's not just one catastrophic event we're looking at, but layers of impacts stacked like chapters in a geological mystery? These nested craters could hold the key to understanding not just how our planet has changed, but why. They might reveal clues about ancient climate shifts, mass extinctions, and even the very building blocks of life itself. This is a journey into the unknown, a dive beneath the surface of our world to uncover the hidden impact zones that have shaped everything around us. We'll explore how cutting-edge technology is revealing these buried secrets, from satellite imaging to deep core drilling. We'll revisit famous craters with fresh eyes and venture into debates that challenge long-held scientific beliefs. Along the way, we'll meet the researchers who are piecing together this cosmic puzzle, one discovery at a time. So buckle up, because what you're about to learn might just change the way you see our planet forever. Picture a rock the size of a mountain hurtling through space at tens of thousands of miles per hour. When it slams into Earth, the energy released is beyond comprehension, equivalent to millions of nuclear explosions in an instant. The ground vaporizes, shockwaves ripple through the planet's crust, and in mere seconds, a gaping wound is carved into the surface. This is how an impact crater is born, a scar left behind by the violent dance between Earth and the cosmos. But not all craters are created equal. Some are simple bowls, like the meteor crater in Arizona, clean, circular depressions formed by smaller, high-speed impacts. Others are complex, sprawling across hundreds of miles with towering central peaks and concentric rings. These form when the impact is so immense that the Earth's crust rebounds like a drop of water hitting a pond, creating ripples frozen in stone. The Redifort crater in South Africa, the largest confirmed impact structure on Earth, is one such masterpiece of destruction, a colossal bullseye telling the story of an asteroid nearly 6 miles wide. Now imagine peeling back the layers of one of these giants and finding another crater hidden beneath. This isn't science fiction, it's a geological detective story. Nested craters occur when a new impact strikes near or directly atop an older one, burying the evidence under debris and time. Over millions of years, wind, water, and shifting continents act like nature's eraser, smoothing away the obvious clues. Sediment fills the basins, forests grow over the ruins, and what was once a glaring wound fades into the landscape. That's where the real sleuthing begins. Scientists use tools straight out of a spy thriller to uncover these hidden histories. Satellite imagery captures subtle variations in gravity and vegetation, revealing circular patterns invisible to the naked eye. Seismic surveys send sound waves deep underground, painting pictures of disrupted rock layers like sonar probing the ocean floor. Sometimes it's pure luck. A mining operation drills into what seems like ordinary bedrock and stumbles upon shattered quartz or exotic minerals that scream cosmic collision. Every discovery is a puzzle piece, helping us reconstruct Earth's explosive past one crater at a time. Deep in the heart of South Africa lies a geological giant so vast it's hard to comprehend, the Redifort crater, stretching over 150 miles wide. Formed more than 2 billion years ago, this ancient scar is Earth's oldest and largest confirmed impact site. But what makes it truly fascinating isn't just its size, it's the whispers of something even older lurking beneath. Recent studies suggest the colossal impact that created Redifort might have struck directly over a pre-existing crater, like a bullseye painted atop an older target. Gravity surveys reveal strange anomalies in the rock layers, hinting at disruptions that don't match a single, clean impact. Could this be evidence of a cosmic 1-2 punch, with one catastrophe buried under another? Half a world away, in the rugged terrain of Ontario, Canada, the Sudbury Basin tells a different but equally compelling story. Discovered during 19th century mining operations, this 37-mile-wide depression was long assumed to be volcanic in origin until geologists found telltale signs of an extraterrestrial collision. Shocked quartz, melted rock, and layers of mineral deposits pointed to a cataclysmic impact nearly 2 billion years ago. But as miners dug deeper, they uncovered something unexpected. The crater's floor wasn't uniform. Instead, it revealed a chaotic jumble of fractured bedrock and strange, isolated pockets of melted material. Some researchers now argue these disruptions aren't just from the original impact, they're remnants of an even older event, a hidden chapter in Earth's violent history rewritten by a second, younger strike. Then there's the Woodley crater in Western Australia, a mystery wrapped in controversy. Initially estimated to be 75 miles wide, later studies suggested it might be as small as 37 miles, or as large as 120. The debate hinges on whether what we see is the full crater or just a fragment of something far grander, with the rest concealed beneath sediment or eroded away. Core samples from the site contain minerals only formed under extreme pressure, but their distribution doesn't match a single, neat impact zone. Could Woodley's chaotic layers be the result of multiple impacts stacked like pages in a book? These three sites, Redifort, Sudbury, and Woodley, paint a startling picture. If even a handful of Earth's known craters hide nested impacts beneath them, our planet's history is far more turbulent than we've imagined. Each layer represents a reset button, a moment when the ground itself was reshaped by forces from beyond our world. And with every new discovery, we're forced to ask, how many other craters are keeping secrets? How many ancient catastrophes have been erased, not by time, but by newer, fresher violence? The answers could rewrite everything we know about Earth's past and our place in the cosmos. Buried beneath the turquoise waters of Mexico's Yucatan Peninsula lies one of Earth's most infamous scars, the Chicxulub crater. This 150-mile-wide behemoth is the smoking gun behind the dinosaurs' demise, a catastrophic event 66 million years ago that rewrote the course of life on our planet. But what if there's more to this story? Recent discoveries suggest Chixulub might not be a singular tragedy. It could be part of a cosmic double feature, with an older impact hidden beneath it like a ghost in the geological record. The clues start with gravity. When scientists mapped subtle variations in Earth's gravitational pull over the crater, they noticed something odd. The readings didn't form a clean, symmetrical pattern. Instead, they revealed irregularities, pockets where the underground rock seemed denser or more fractured than expected. These anomalies line up with core samples pulled from deep beneath the seafloor, where layers of melted rock and shattered minerals tell a chaotic tale. Some researchers argue this disruption isn't just from the dinosaur-killing impact. It's evidence of an earlier collision, one that struck the same bullseye millions of years before Chicxulub's asteroid arrived. Then there's the fossil record. The boundary between the Cretaceous and Paleogene periods, marked by Chicxulub's impact, shows a sudden die-off of species but also puzzling gaps. Some sediments contain strange mineral mixtures that don't match a single, clean asteroid strike. Could these inconsistencies be explained by two impacts? Picture this: one asteroid strikes, triggering volcanic eruptions and climate shifts. Then, before ecosystems can recover, another hits, compounding the devastation. It's a theory that could explain why some species vanished earlier than others, or why certain regions show more extreme environmental changes than the rest of the planet. The implications are staggering. If Chicxulub is hiding an older sibling, it means Earth's history of cosmic violence is even more complex than we thought. It raises questions about how often asteroids arrive in pairs or clusters, and whether our planet's greatest extinctions were caused not by lone disasters, but by 1-2 punches from the cosmos. For scientists, this isn't just about rewriting the past, it's a warning. If double impacts are possible, our strategies for predicting and deflecting future threats might need rethinking too. Right now, teams are racing to drill deeper into Chicxulub's secrets, hunting for definitive proof of this hidden impact. Every layer of rock they peel back is like turning a page in Earth's autobiography, and the next chapter could change everything. The ground shakes, the sky darkens, and within moments the planet's climate is thrown into chaos. This isn't a scene from a disaster movie, it's what happens when a massive asteroid strikes Earth. But when impacts occur in layers, one atop another, the environmental consequences multiply in ways we're only beginning to understand. Hidden within these nested craters are chemical time capsules, preserving clues about ancient climate catastrophes that reshaped life on our planet. Take the case of the Popogai crater in Siberia, a 56-mile-wide scar formed 35 million years ago. Core samples from its depths reveal something startling: layers of carbon-rich sediment mixed with minerals that only form under extreme heat. Paleoclimatologists studying these deposits suspect the impact ignited vast coal deposits, releasing torrents of carbon dioxide and methane into the atmosphere. The result, a sudden spike in global temperatures, compounding the cooling effects of impact debris already blocking sunlight. This 1-2 punch of fire and ice could explain why the Eocene-Oligocene extinction event was so severe, an ecological collapse driven not just by a single catastrophe, but by cascading environmental disasters. Then there's the Deccan traps in India, one of Earth's largest volcanic provinces. For decades, scientists debated whether its eruptions coinciding with the Chicxulub impact were triggered by seismic waves from the asteroid strike. But newer theories suggest a twist. What if the Deccan traps sit atop an even older, buried crater? Gravity anomalies and unusual mineral formations hint at a colossal impact predating the volcanoes. If true, this hidden collision could have fractured Earth's crust, creating weak points where magma surged upward millions of years later. The implications are staggering. A single impact might alter climate for decades, but a nested one could destabilize the planet's geology for millennia, turning the thermostat up and down like a broken dial. Modern climate models are now incorporating these ancient disasters to predict our future. By analyzing isotopes in crater sediments, researchers can track how past greenhouse gas releases compare to today's human-driven emissions. The parallels are unnerving. The carbon released by the Popogai impact's coal fires was roughly equivalent to 20 years of current industrial output, but it happened in days, not decades. That suddenness caused ecosystems to collapse faster than species could adapt. Today, as we drill into craters like Chesapeake Bay or Mistastine Lake, we're finding similar patterns: layers of soot, acid rain residues, and fossilized pollen showing abrupt vegetation shifts. These aren't just relics of the past, they're roadmaps, showing us how quickly climate can spiral when pushed past tipping points. The real breakthrough came when scientists started connecting crater chemistry to ice cores. In Antarctica, mile-deep ice preserves snapshots of ancient atmospheres, and when matched with impact layers, they reveal a disturbing trend. Every major crater corresponds to wild swings in temperature and gas concentrations. But the most extreme shifts align with sites where multiple impacts are suspected. It's as if Earth's climate can handle a single knockout punch, but when strikes come in clusters, the system falters. This research is more than academic. It's helping climatologists refine predictions about how modern ecosystems might respond to rapid changes, whether from asteroids or human activity. What emerges from these hidden impact zones is a story of resilience and fragility. Our planet has endured cosmic bombardments that dwarf anything in human history, yet life always finds a way to rebound. But these recoveries take time, sometimes millions of years. As we uncover more nested craters and decode their climate secrets, one lesson becomes clear: Earth's history isn't just written in rock. It's etched into the very air we breathe, a reminder that the forces shaping our world are far older and far more powerful than we often realize. Peering beneath Earth's surface to uncover hidden craters used to mean relying on luck, a chance outcrop of strange rocks or a farmer's plow hitting something unusual. Today, scientists wield tools that feel borrowed from science fiction, allowing them to scan landscapes with near-magical precision. At the forefront is LiDAR, a laser-based technology that strips away forests and vegetation like an X-ray, revealing the naked topography beneath. When researchers deployed LiDAR over the dense jungles of Central America, they didn't just find ancient ruins. They stumbled upon circular depressions that turned out to be previously unknown impact craters, masked for centuries by thick canopies. Ground-penetrating radar takes the search even deeper, sending pulses of energy into the Earth that bounce back to paint pictures of buried structures. Unlike traditional digs, which might miss subtle layers, this tool captures disruptions in rock formations invisible to the human eye. In Australia's outback, radar waves expose the contours of the Wolf Creek crater beneath layers of wind-blown sand, showing fractures that hint at multiple impact events stacked over time. But the real game-changer is artificial intelligence. Machine learning algorithms sift through terabytes of satellite data, flagging anomalies like faint circular patterns in gravitational fields that human researchers might overlook. When NASA trained AI to scan Greenland's ice sheet, it identified the Hiawatha crater, a 19-mile-wide impact site hidden under a half-mile of ice. The kicker, the crater's pristine state suggests it's geologically young, possibly formed as recently as 12,000 years ago, rewriting theories about Earth's recent cosmic encounters. Yet these high-tech methods aren't flawless. LiDAR struggles with reflective surfaces like water, and radar signals get muddied by dense clay or volcanic rock. AI, for all its brilliance, can generate false positives, interpreting ancient volcanic calderas or eroded riverbeds as potential craters. Even when tools detect something promising, confirmation requires boots on the ground. Teams still brave polar ice, deserts, and jungles to collect rock samples, proving whether a suspicious circle is truly a cosmic wound or just a trick of geology. The irony, for all our advancements, some of the most exciting discoveries still come from amateurs like the Australian farmer who noticed strange, glassy rocks in his field, leading to the recognition of the 15-mile-wide Deniliquin crater. The hunt for hidden craters is a dance between cutting-edge tech and old-fashioned grit. Every tool has blind spots, and every discovery raises new questions. But with each technological leap, we peel back another layer of Earth's violent history, one impact at a time. Finding hidden craters is like playing the ultimate game of hide and seek, except the hiders have millions of years and entire continents working in their favor. Thick rainforests drape impact sites in green camouflage, while sprawling cities pave over ancient scars with concrete and steel. Even the ocean, covering 70% of our planet, swallows cosmic collisions whole, leaving only faint traces in seafloor sediments. But perhaps the greatest adversary isn't geography, it's time itself. Wind, rain, and tectonic shifts constantly reshape the surface, erasing craters grain by grain until only subtle clues remain. Take erosion, nature's ultimate eraser. A fresh crater might stand out like a sore thumb, but after millions of years, its rim gets worn down, its bowl fills with sediment, and what was once a gaping wound blends into the landscape. The Canadian Shield, home to some of Earth's oldest rocks, illustrates this perfectly. Glacial ice sheets scoured the region repeatedly, smoothing away surface features like sandpaper on wood. Only the deepest, most resilient craters like Sudbury survived this geological sandblasting. Elsewhere, rivers and floods act like conveyor belts, carrying debris into impact basins until they're buried under thousands of feet of silt. The Woodford crater in Oklahoma, it lay hidden for 300 million years until oil drillers accidentally punched through its disguised layers. Urbanization adds another layer of difficulty. Imagine trying to spot a crater beneath London or New York. Not impossible, but like searching for a needle in a skyscraper-filled haystack. Construction projects rarely dig deep enough to expose ancient impact zones, and when they do, the evidence is often misinterpreted. The Rise crater in Germany was mistaken for volcanic activity until the 1960s, even though villages had been built right inside its rim. Roads, farms, and forests create a patchwork that obscures the big picture, leaving researchers to piece together fragments like a jigsaw puzzle missing half its pieces. Then there's the ocean's cloak of invisibility. Water doesn't just hide craters, it actively destroys them. Currents redistribute sediments, underwater landslides smear out features, and the relentless pressure of the deep helps compact and distort impact signatures. The Eltonin impact, the only confirmed deep-sea crater, was found purely because oceanographers were studying Antarctic ocean currents and noticed strange mineral grains in their samples. Most oceanic impacts leave no visible scar at all, just chemical traces in sediment cores or distant tsunami deposits on shorelines. Yet sometimes, against all odds, fortune smiles on science. The Chesapeake Bay crater, one of the best-preserved marine impacts on Earth, was discovered in the 1990s not by geologists but by an oil company drilling test wells. Their cores brought up fractured rock and melted minerals that screamed cosmic collision, revealing a 53-mile-wide crater buried under half a mile of sediment. Similar accidents have rewritten textbooks. A mine in South Africa exposed the Redifort crater's hidden layers, while road cuts in Scandinavia revealed the Lockney impact structure. These moments of serendipity remind us that for all our advanced tools, discovery still depends on curiosity and sometimes pure dumb luck. The hunt for hidden craters isn't just about technology or patience. It's about recognizing that Earth's surface is a palimpsest, a parchment scraped clean and reused over and over. Every crater found, whether by satellite or stumble, adds another line to the story. And with each revelation, we're forced to ask, how many more are waiting, quietly reshaping our understanding of the past? Eugene Shoemaker didn't just study craters, he made the world see them differently. In the 1950s, when most geologists dismissed meteor impacts as rare and insignificant, Shoemaker saw something revolutionary. While mapping Arizona's meteor crater, he noticed something textbooks couldn't explain: shocked quartz and coesite, minerals that only form under pressures found in nuclear blasts or cosmic collisions. His findings shattered the prevailing belief that Earth's scars were volcanic, not extraterrestrial, but the scientific establishment didn't roll out the red carpet. For years, Shoemaker faced skepticism, even ridicule, as he argued that asteroids had shaped our planet far more than anyone realized. His persistence paid off. By the time NASA needed someone to train Apollo astronauts in lunar geology, Shoemaker was the obvious choice, though a medical condition tragically barred him from space. His legacy, a paradigm shift, proving that Earth's surface is a battlefield in an ongoing cosmic war. Modern crater hunters stand on Shoemaker's shoulders, but their tools are anything but old school. Take Dr. Ludovic Ferrier, curator at Vienna's Natural History Museum, who combines geology with forensic science. When a farmer in Egypt stumbled upon strange glass fragments in the desert, Ferrier's team identified them as Libyan desert glass, melted sand from a 28-million-year-old impact. But the crater itself was missing. Using satellite data and field surveys, they pieced together a puzzle. The glass was debris from a hypervelocity strike so violent it vaporized the asteroid before it could leave a traditional crater. This kind of interdisciplinary detective work, blending chemistry, physics, and remote sensing, is rewriting the rules of impact science. Then there's Dr. Natalia Artemieva, a computational dynamo who models impacts with supercomputers. Her simulations revealed how the Chicxulub asteroid didn't just explode on impact, it punched a hole through Earth's crust, triggering volcanic chains and climate chaos. Artemieva's work bridges astronomy and paleoclimatology, showing how cosmic events ripple through millennia. Meanwhile, in Australia, Dr. Andrew Glickson pores over ancient rock layers, hunting invisible craters erased by time. His secret weapon, isotopes, by tracing extraterrestrial elements like iridium in sediments, he's identified potential impact sites older than life itself, like the 3-billion-year-old Yarrabubba structure, proof that Earth's earliest eons were just as violent as its recent past. What unites these researchers isn't just curiosity, it's a willingness to challenge dogma. When Dr. Sarah Majari proposed that Iran's Tabriz Desert hid a nested crater system, skeptics scoffed. Then her team found concentric fractures in seismic data, backed by mineral evidence of multiple impacts. Today, Tabriz is a textbook example of how planetary violence leaves layered fingerprints. Similarly, Dr. Gordon Osinski studies impact craters as astrobiological labs, arguing that the heat and chemistry of collisions could have jump-started life's building blocks. His fieldwork in Canada's Horton crater, a Mars analog, fuels theories that impacts don't just destroy, they might create habitats for extremophiles. The lesson from these pioneers: progress in crater science often starts on the fringes. Whether it's Shoemaker fighting for recognition or modern teams blending AI with old-school fieldwork, the hunt for hidden impacts thrives on bold thinking. Every discovery chips away at the illusion of Earth as a tranquil oasis, revealing instead a world shaped by celestial violence and the stubborn brilliance of those who dare to dig deeper. Long before telescopes or seismographs, ancient cultures gazed at the sky and Earth, weaving stories to explain the inexplicable. Among Australia's Aboriginal peoples, oral traditions speak of a firestar that fell from the heavens, igniting the land and leaving behind gaping wounds in the earth. These tales, passed down for thousands of years, describe events eerily similar to meteor impacts, complete with fiery trails, thunderous booms, and circular scars. Some researchers now suspect these legends might preserve memories of real cosmic collisions, like the Henbury craters in the Northern Territory. where 12 impact sites dating back 4,700 years coincide with local Dreamtime stories of a celestial ironwood club striking the ground. Could these narratives be humanity's first records of nested impacts, where one catastrophic event layered atop another in collective memory? Half a world away, Norse mythology paints a chilling parallel. The Prose Edda, a 13th century Icelandic text, describes the creation of the world from the body of the giant Ymir, his flesh becoming land, his blood the seas, and his skull the sky. But buried in these poetic images are hints of chaos. The gods slay Ymir with such force that his bones shatter like ice, and his blood floods the earth. Some scholars argue this mirrors geological upheaval, perhaps even the aftermath of a colossal impact. The Norse weren't alone. The Babylonian epic of Gilgamesh speaks of 7 judges of hell who rain fire upon the earth, while Hopi traditions in North America recount a time when the sky cracked open, hurling molten rocks onto the land. These aren't just metaphors. When archaeologists compare these accounts to known impact sites, the overlaps are uncanny. The Colli crater in Estonia, formed 2,500 years ago, sits at the heart of local folklore about a sun god's chariot crashing to Earth, a story that aligns with the crater's sudden, searing formation during the Bronze Age. The challenge lies in separating myth from memory. Oral traditions are fluid, adapting over centuries, but certain details, like the direction of a fireball's path or the shape of the devastation, often persist with startling accuracy. Dr. Dwayne Hamacher, an indigenous astronomy scholar, has documented how Aboriginal elders in Victoria describe celestial events with precision, including the exact position of a falling star that matches the location of an ancient impact crater. Similarly, in the Sahara, Tuareg tribes speak of the day the sky split, a legend that aligns with the discovery of the Kibera crater, a 19-mile-wide structure eroded but still visible from space. These stories aren't just curiosities, they're potential roadmaps guiding scientists to overlooked impact sites based on ancestral knowledge. The intersection of astrophysics and archaeology is yielding even more tantalizing clues. Take the Mahabharata, an ancient Indian epic that recounts a cataclysmic battle with weapons brighter than 1,000 suns, leaving lands barren and rivers boiling. For years, these passages were dismissed as poetic exaggeration, until geologists found a layer of radioactive ash in Rajasthan, dating to roughly the same era as the text. Nearby, the Lonar crater, a 50,000-year-old impact site, holds water so alkaline it's compared to the poisoned lakes described in the epic. Coincidence, maybe, but as researchers cross-reference more legends with geological data, patterns emerge. The key is in the details. When multiple cultures separated by continents describe similar events like prolonged darkness, global fires, or rains of stones, it's worth asking whether they're recalling shared trauma from cosmic violence. What makes these connections so compelling isn't just the possibility that ancient peoples witnessed impact. It's the idea that they might have recorded multiple layers of catastrophe. The Greek myth of Phaethon, who loses control of the sun chariot and scorches the earth, could reflect a memory of wildfires triggered by an impact, but earlier versions of the story, found in Egyptian papyri, add another layer, a second sun that appears in the sky before the disaster. Could this be an observation of a fragmented asteroid, with one piece striking first and another following? Similarly, Chinese astronomers in the first millennium BC documented guest stars, sudden bright lights in the sky, that modern researchers now link to possible meteor showers or airbursts. When these records are paired with sediment cores showing iridium spikes or glassy spherules, the case for nested impacts grows stronger. Yet for all their richness, myths alone can't rewrite scientific history. The real breakthrough comes when stories meet hard evidence like the discovery of nanodiamonds in the Greenland ice sheet, matching the timeline of a medieval European famine once blamed on demonic comets, or the way Maya codices depict a sky serpent spewing fire, a symbol that aligns with sediment layers from a suspected Caribbean impact around the 9th century CE. These threads, oral tradition, written records, and physical traces form a tapestry that's still being unraveled. Every crater found, whether through satellite data or ancestral wisdom, adds another stitch, pulling us closer to understanding how deeply cosmic chaos is woven into human history. The next time you hear an old tale about gods hurling fire from the heavens, consider this. Our ancestors might have been the first crater hunters, their stories a survival guide for a planet caught in the crosshairs of the cosmos. And as science catches up to their wisdom, we're left to wonder what other truths lie hidden in the myths we've yet to decode. When an asteroid slams into Earth, it doesn't just leave a hole in the ground, it stamps the planet with a chemical signature as unique as a fingerprint. These geochemical smoking guns, hidden in layers of rock and sediment, tell stories of cosmic violence that even the most eroded craters can't conceal. Take shocked quartz, a mineral that forms only under pressures found in nuclear explosions or asteroid impacts. Its telltale crisscrossed pattern under a microscope is like a cosmic calling card, proving a rock was blasted by forces beyond anything Earth's geology can produce naturally. But the real magic happens when scientists find these minerals arranged in distinct layers like pages in a book, each marking a separate impact event. Then there's iridium, the element that cracked open the dinosaur extinction mystery. Rare in Earth's crust but abundant in asteroids, a sudden spike in iridium concentrations is like finding a fleck of paint from a hit-and-run driver at a crash site. When researchers drilling into the Popogai crater in Siberia found not one but two iridium-rich layers separated by millions of years of sediment, it was proof that this 60-mile-wide scar held a secret a second older impact buried beneath. The chemistry didn't stop there. Isotopes of osmium and chromium, elements with distinct cosmic ratios, painted a picture of two different asteroids striking the same bullseye across geologic time. Like a detective matching bullet fragments to guns, geochemists can now trace these elements back to different types of space rocks, revealing whether multiple impacts came from the same asteroid family or unrelated celestial wanderers. But the most startling clues come from things that shouldn't exist at all. Diamonds, for instance, not the glittering gems of jewelry stores, but tiny, misshapen crystals forged in the hellish pressures of an impact. The Popogai crater is littered with them, formed when the asteroid's shockwave instantly compressed graphite deposits into diamond. Here's the twist: these aren't uniform. Some layers contain diamonds with structural defects seen only in ultra-high pressure lab experiments, while others show signs of being reheated, evidence that the second impact cooked the diamonds left by the first. It's as if the crater kept receipts for each cosmic catastrophe, preserving receipts in atomic detail. The same forensic approach is rewriting history at Mexico's Chicxulub crater. Core samples pulled from beneath the Gulf seabed show alternating bands of melted rock, some rich in nickel from the asteroid's core, others packed with sulfur from vaporized seabed deposits. These alternating layers suggest periods of calm between impacts, time for the ocean to partially refill the crater, only to be blasted away again. Even the glassy spherules found worldwide from the dinosaur-killing event have siblings smaller, chemically distinct spheres buried deeper, hinting at an earlier impact that shook the planet before Chicxulub's coup de grace. What makes these geochemical fingerprints so powerful is their resistance to time. While craters fade and fossils crumble, elements like iridium and minerals like shocked quartz endure. They're silent witnesses to Earth's most violent moments, waiting in the strata for scientists with the right tools to decode their stories. And as we learn to read these signatures more precisely, a startling pattern emerges. Our planet's history isn't just marked by occasional cosmic accidents, but by chapters of repeated bombardment, a rhythm of destruction written in atoms, not words. Now consider what these layered cataclysms meant for life on Earth. If a single impact like Chicxulub could wipe out 75% of species, what happens when disasters stack like dominoes? The answer lies in the rocks and the fossils trapped between them. The fossil record reads like a chronicle of apocalypse's 5 mass extinctions where life on Earth teetered on the brink, each marked by sudden collapses in biodiversity. For decades, scientists pointed to single catastrophic events as the culprits: a colossal asteroid for the dinosaurs, volcanic eruptions for the Permian-Triassic die-off. But what if these weren't standalone disasters? A growing body of evidence suggests that nested craters, multiple impacts stacked in geological layers, might tell a darker story. That Earth's worst die-offs were triggered not by one cosmic blow, but by several in rapid succession. Take the end Permian extinction 252 million years ago, when 96% of marine species vanished. The traditional villain is the Siberian traps, monstrous volcanic eruptions that choked the atmosphere with CO2. But drill cores from Antarctica reveal something unsettling. Microtectites, tiny glass beads formed from molten rocks splashed by impacts, layered right alongside volcanic ash. These beads don't match the trap's chemistry, they're foreign, likely from a meteor strike. Meanwhile, in South Africa's Karoo Basin, fossils show 2 distinct pulses of death. First, a slow decline from climate shifts, then a sudden crash coinciding with the tektite layer. The implication: while volcanoes set the stage, an impact may have delivered the killing blow. Or perhaps multiple strikes, with their craters since buried or eroded away. The Cretaceous-Paleogene KPG boundary, famous for dooming the dinosaurs, hides similar clues. Yes, Chicxulub's asteroid was the headliner, but sediment layers from New Zealand to Spain contain 2 iridium spikes, not one. The first aligns with Chicxulub's impact 66 million years ago. The second, slightly fainter, appears roughly 100,000 years later. Some researchers argue this could mark a second, smaller impact, compounding the ecological chaos. Imagine a planet already reeling from years of darkness and cold, its food chains shattered when another asteroid strikes, reigniting the devastation. Fossil pollen tells this tale vividly. After the first impact, hardy ferns dominate, a classic sign of ecosystems rebooting. But in some regions, this fern spike is abruptly interrupted by another layer of barren soil, suggesting recovery was cut short by a second catastrophe. Then there's the impact winter hypothesis, where dust and sulfur from collisions blot out the sun, triggering global cooling. Models show a single large impact can plunge temperatures by 20 degrees Celsius for a decade. But when scientists simulated double impacts 2 strikes years or centuries apart, the results were chilling. The second impact amplifies the first, like throwing gasoline on smoldering embers. Sulfur from the new collision mixes with lingering atmospheric debris, extending the winter's duration. Ocean circulation stalls, turning seas anoxic. Plants already struggling with reduced sunlight face acid rain from the fresh impact's fallout. It's a recipe for total ecosystem unraveling, where species surviving the first blow succumb to the compounding stresses of the next. The timeline of known craters adds weight to this grim picture. The late Triassic extinction, 201 million years ago, coincides with the Manicouagan crater in Canada, a 60-mile-wide scar. But dig deeper and you find the Chixulub crater in France formed around the same time. Were these part of an asteroid shower, like the 1994 comet fragments that bombarded Jupiter? Similarly, the Eocene epoch, 56 million years ago, shows 4 impact craters within a 2-million-year window, a geological blink. Paleontologists note this period saw dramatic mammalian turnover, with ancient lineages vanishing as new ones emerged. Coincidence or evidence that life's trajectory was reshaped by serial cosmic violence? Critics argue that correlation isn't causation, that random alignments of craters and extinctions are inevitable over Earth's vast timeline. But proponents counter with geochemical fingerprints. The Deccan Trap's lava flows, once blamed solely for the KPG extinction, contain platinum group metals matching asteroid composition, hinting at concurrent impacts. In Montana's Hell Creek Formation, dinosaur fossils appear right up to the KPG boundary, except in a thin layer just below it, where bones vanish abruptly. This 3-meter gap suggests some species were already dwindling before Chicxulub, possibly due to earlier environmental shocks. The stakes of this debate couldn't be higher. If mass extinctions were driven by clustered impacts rather than lone disasters, it reshapes our understanding of cosmic threats. Modern asteroid detection programs focus on large, civilization-ending rocks, but what if the real danger lies in smaller, multiple strikes? The Tunguska event of 1908, a meteor airburst over Siberia, flattened 800 square miles of forest. Had it struck a century later, during the Cold War, the blast might have been mistaken for a nuclear attack. Now imagine 2 such events decades apart, or a stealth impact in the ocean, triggering tsunamis during global crop failures from a prior strike. As we peer deeper into Earth's cratered past, one unsettling pattern emerges. Our planet's history isn't just punctuated by random cosmic bullets, it may have endured volleys. And if that's true, humanity's survival strategies might need to look beyond deflecting a single doomsday rock, toward preparing for the possibility that sometimes the heavens open fire. Beneath the rolling waves that blanket our planet lies a hidden battlefield, a graveyard of cosmic collisions erased by time and tide. While land craters like Chicxulub or Vredifort dominate headlines, the real frontier of impact science unfolds in Earth's oceans, where 70% of asteroid strikes leave barely a trace. The challenges here are immense. Water absorbs shock waves, sediments bury evidence, and shifting currents scatter debris like cosmic breadcrumbs. Yet the few oceanic craters we've uncovered rewrite history with every discovery. Take the Eltonin impact, a 2.5-mile wide scar 2.5 miles beneath the Pacific, found accidentally in 1965 when oceanographers hauled up odd mineral grains from the seafloor. It's the only confirmed deep-sea crater on Earth. But here's the twist: core samples revealed it wasn't a direct hit. The asteroid likely vaporized upon entering the ocean, detonating with the force of 1 million Hiroshima bombs and triggering tsunamis that left traces in Antarctic ice layers. This underwater airburst suggests we might be missing dozens of similar events, their craters non-existent but their global effects catastrophic. Now picture something even more elusive: nested impacts beneath the waves. If terrestrial craters can hide older siblings under their rims, why couldn't oceanic ones? The problem is scale. While land craters leave mineral fingerprints, ocean impacts dissolve evidence in saltwater chemistry. A strike like Eltonin's could erase traces of an older crater beneath it, leaving only chemical ghosts like the iridium anomalies found in mid-Atlantic ridge sediments, far from any known impact site. Some researchers speculate these could mark invisible nested strikes, where younger impacts reset the oceanic record. The clues might lie in methane. When asteroids plow into methane-rich seabeds, They can trigger monstrous gas releases like the Storegga slides off Norway, where submarine landslides unleashed tsunamis 8,000 years ago. If impacts caused similar collapses, their nested signatures could be locked in methane hydrate layers, waiting for drills to uncover them. The implications stretch beyond science. Oceanic craters are treasure chests of rare minerals forged in the furnace of impact pressures. The Eltonin site contains asteroid-derived platinum and gold particles scattered across the seafloor, a potential mining bonanza. But the real jackpot might be hydrogen. When seawater reacts with impact-heated rock, it generates vast hydrogen stores, a clean energy source that could power nations. Japan's deepest drills have already found hydrogen-rich zones near suspected impact sites. Yet harvesting these resources risks destroying the very craters that hold them, sparking ethical dilemmas. Should we mine these cosmic time capsules for short-term gain, or preserve them as archives of Earth's survival? Every wave that rolls ashore carries whispers of these hidden collisions. From tsunamis that reshaped ancient coastlines to methane burps that altered climates, oceanic impacts are the silent architects of our past, and perhaps the key to our future. As sonar maps grow sharper and robots probe deeper, who knows what shattered craters might emerge from the abyss, rewriting our place in the cosmos once more. Beneath the shattered rock of ancient impact craters lies a paradox destruction that births treasure. When asteroids collide with Earth, they unleash forces so extreme they rearrange the very chemistry of the planet's crust, creating pockets of concentrated wealth. The Sudbury Basin in Canada, a 37-mile-wide scar from a 2-billion-year-old impact, exemplifies this phenomenon. What began as a cataclysmic explosion became one of the world's richest nickel deposits, with mines extracting millions of tons of ore, alongside platinum, copper, and gold. The secret: the impact's unimaginable heat and pressure melted Earth's mantle, allowing heavy metals to pool like liquid in a cosmic crucible. But Sudbury's real surprise came when miners dug deeper, uncovering not one uniform layer of metal, but multiple distinct zones of mineralization. Geologists now believe these stratified riches hint at something extraordinary: the possibility that Sudbury's asteroid struck an even older impact site, its pre-existing fractures and molten pools creating the perfect trap for metal-rich magma. Diamonds tell a similar story. Most gem-quality diamonds form slowly over billions of years in Earth's mantle, but impact diamonds are born in seconds. The Popogai crater in Siberia, a 56-mile-wide scar from a 35-million-year-old strike, holds trillions of carats of diamonds, forged when the asteroid's shockwave compressed graphite deposits instantly. Unlike traditional diamonds, these are microscopic, with a hardness that makes them ideal for industrial cutting tools. But here's the twist: some Popogai diamonds show unusual structural defects, suggesting they endured not one, but multiple shockwaves. Could this mean the crater sits atop an older impact zone, its hidden fractures guiding the formation of these ultra-hard crystals? The same pattern emerges in South Africa's Redifort crater, where gold deposits align eerily with the concentric rings of the impact structure, as if the asteroid's violence herded precious metals into geologic corrals. Then there's oil, the unlikely child of cosmic collisions. Most petroleum forms from ancient algae buried under sediment, but impact craters can supercharge the process. The Chicxulub crater, infamous for killing the dinosaurs, also sits atop one of Mexico's largest offshore oil fields. The reason? The asteroid's heat cooked organic material in the Yucatan's limestone at record speed, while its fractures created porous reservoirs for oil to accumulate. Similar discoveries in the Chesapeake Bay and Rise craters suggest these structures act like natural pressure cookers, turning millennia of slow geological processes into centuries or even decades. Yet this bounty comes with ethical dilemmas. Mining operations at Sudbury have unearthed invaluable geological evidence, like layers of shocked quartz that rewrite impact theories, only to destroy them in the pursuit of nickel. At Poppyguy, diamond extraction threatens to erase chemical clues about Earth's ancient atmosphere preserved in the crater's rocks. The tension is clear. These sites are both economic gold mines and irreplaceable scientific archives. Some propose compromise solutions like Canada's Creighton mine, where researchers work alongside miners to document fossils and rock layers before they're processed for metal. Others advocate for impact preserves, where select craters remain untouched as planetary time capsules. The challenge mirrors debates over rainforests or coral reefs, how to balance human needs with the preservation of natural wonders that tell our planet's story. Perhaps the answer lies in seeing these crater resources not just as commodities, but as chapters in Earth's biography. After all, every ton of Sudbury nickel carries traces of an asteroid that reshaped the planet, and every Poppyguy diamond holds the echo of a cosmic detonation. In their glitter and sheen, we're not just extracting wealth, we're holding fragments of the universe itself. In the world of crater science, few debates ignite as much passion as the Shiva hypothesis, a theory as dramatic as the cosmic collision it proposes. Picture this: beneath the waves off India's western coast lies what some researchers believe could be one of Earth's largest impact craters, a 300-mile-wide behemoth they've named Shiva. Its advocates argue this hidden giant struck 66 million years ago, around the same time as Chicxulub, triggering the Deccan traps, a million-year volcanic eruption that spewed enough lava to bury Texas half a mile deep. The implications are staggering: not one but two simultaneous catastrophes, an asteroid from above and volcanic hellfire from below, teaming up to wipe out the dinosaurs. Mainstream geologists aren't convinced. The evidence for Shiva rests on gravity anomalies and seismic data showing what might be a crater's outline, but critics point out these could just as easily be ancient rift zones or tectonic folds. The smoking gun, shocked quartz or iridium spikes hasn't materialized, and core samples from the Deccan traps lack definitive impact markers. Skeptics like Dr. Gerta Keller, a Princeton geologist, argue the volcanic activity started well before the extinction event, making Shiva an unnecessary complication. Extraordinary claims require extraordinary evidence, she says, echoing the scientific community's cautious mantra. Yet the Shiva camp, led by charismatic figures like geophysicist Sankar Chatterjee, counters with circumstantial clues. They note the Deccan traps' lava flows are unusually rich in metals like platinum and osmium, elements more common in asteroids than Earth's mantle. Then there's the timing. The volcano's most violent phase coincides precisely with the KPG extinction boundary. Chatterjee's team even points to computer models showing how an impact in the Indian Ocean could have sent seismic waves rippling through the planet, cracking open magma chambers like an egg. For them, Shiva isn't just a crater, it's the missing piece that solves the dinosaur puzzle. The battle plays out in academic journals and conferences where peer review becomes a high-stakes game. When a pro-Shiva paper surfaces, critics pounce on its methods. When skeptics publish counter-arguments, Shiva supporters accuse them of dismissing data too hastily. The irony: both sides agree on one thing: Earth's geologic record is incomplete. The real conflict isn't just about evidence, it's about how we fill in the gaps. Do we extrapolate boldly from fragmentary clues, or wait for ironclad proof that may never come? What makes this debate so fascinating isn't who's right or wrong, it's how science self-corrects. Every few years, new tools shift the balance. advanced seismic imaging might one day map Shiva's hypothetical rim in detail. Deep-sea drones could scour the ocean floor for impact ejecta. Already, studies of lunar craters hint that double impacts might be more common than we thought, reviving interest in Earth's potential twin scars. Until then, the Shiva hypothesis lingers in that thrilling gray area where fringe ideas either crumble or become consensus. And that's the heart of crater science's greatest controversy, the tension between imagination and rigor. For every Shiva-like theory that fades, another might emerge, a hidden crater waiting to rewrite history. The next paradigm shift could be buried in data we've already collected or in a rock sample yet to be drilled. One thing's certain, as long as Earth's scars keep secrets, the debates will rage on. The hunt for Earth's hidden craters is entering a new era, one where the tools of exploration aren't just pickaxes and seismographs, but rovers, satellites, and the collective curiosity of millions. NASA Artemis program, aiming to return humans to the moon by 2026, isn't just about lunar footprints. Scientists are eager to compare fresh lunar craters with Earth's eroded ones, using the moon as a pristine laboratory. Without weather or tectonics to erase them, lunar craters preserve impact physics in perfect detail, offering clues to how nested structures form. Already, the Lunar Reconnaissance Orbiter has mapped thousands of moon craters, some with strange double rims that might mirror Earth's buried multi-impact sites. These findings could rewrite the rulebook for spotting hidden craters back home, teaching us what subtle gravitational or mineral signatures to chase. Meanwhile, Mars rovers like Perseverance are unintentionally advancing Earth's crater science. The red planet's Jezero crater, a 28-mile-wide ancient lakebed, shares eerie similarities with Earth's Sudbury Basin. Both show layered sediments hinting at repeated upheavals. By studying Jezero's rock layers, scientists are refining techniques to distinguish impact debris from volcanic or sedimentary deposits, methods they'll bring back to Earth. But the real game changer might be under the ice. Antarctica's Wilkes Land anomaly, a 250-mile-wide gravitational oddity buried under a mile of ice, has long puzzled researchers. Some suspect it's a colossal impact crater twice the size of Chicxulub, possibly linked to the Permian extinction. Planned ice-penetrating radar missions, like the European Space Agency's Polar GP, could soon confirm whether this frozen ghost is one of Earth's greatest unconfirmed cataclysms. Yet the most revolutionary crater hunters might be sitting at home in their pajamas. Platforms like NASA's A Cosmic Watch and Zooniverse's Moon Zoo enlist amateur scientists to scan satellite images for circular anomalies or mineral patterns missed by algorithms. In 2021, a German schoolteacher analyzing Google Earth data spotted a previously overlooked circular depression in the Amazon, now a candidate impact site under investigation. Projects like these tap into a global brain trust where eagle-eyed volunteers cross-reference old maps, indigenous oral histories, and even declassified Cold War spy satellite photos. The democratization of discovery means the next great crater might not be found by a PhD with a drill, but by a retiree in Oslo or a teenager in Mumbai, clicking through images on their lunch break. The future of crater science is collaborative, blending interplanetary missions with crowd-sourced curiosity. As AI refines its ability to flag anomalies and expeditions push into Earth's last uncharted frontiers, we're on the verge of a golden age, one where every patch of land or seafloor could reveal a scar from the cosmos. The question isn't whether we'll find more hidden craters, but how many layers of Earth's violent past remain waiting, silent and unseen, for their moment to rewrite history. Imagine teaching a computer to recognize the scars of cosmic violence, not by programming it with rigid rules, but by letting it learn from thousands of examples like a child memorizing constellations. That's the power of artificial intelligence in crater detection. Machine learning algorithms trained on vast libraries of satellite images and radar data now spot patterns so subtle they escape even the most seasoned geologists. In 2021, a team at the University of Toronto fed an AI system low-resolution images of the Moon's surface. Within hours, it identified over 6,000 previously unnoticed microcraters, tiny pockmarks from long-forgotten asteroid strikes, some no larger than a city block. Human researchers would have needed decades to catalog them all, but AI's real genius lies in seeing what we can't. Traditional crater mapping relies on circular shapes, but erosion and tectonic shifts distort older impacts into irregular blotches. Machine learning ignores these biases, detecting craters by their mineral composition, gravitational quirks, or even the way vegetation grows over them. In Australia's outback, an algorithm analyzing Landsat data found the 15-mile-wide Crawford crater, not by its shape, which was eroded to near invisibility, but by the unique way eucalyptus trees avoided its iron-rich soil. Similar breakthroughs are unfolding on Mars, where AI sifts through terabytes of rover images, flagging potential impact sites for closer study. The European Space Agency's Mars Express orbiter recently confirmed an AI-predicted crater hidden under dust deposits, its rim visible only in thermal infrared. Yet for all its precision, AI walks a tightrope between discovery and overreach. In 2022, a much-touted algorithm scanning Greenland's ice claimed to find 7 new craters until glaciologists pointed out it had mistaken meltwater ponds for impact scars. The problem: the AI was trained mostly on desert craters, lacking context for icy environments. This blind spot underscores a deeper debate. Can algorithms ever replicate the intuition of a human scientist who notices odd mineral veins near a crater's edge or connects local folklore to a suspected impact site? Dr. Julia Smith, a planetary geologist at Caltech, argues that AI excels at pattern recognition but falters at synthesis. It can spot 1,000 craters, she says, but won't pause to wonder why 2 identical-looking craters have completely different erosion patterns unless we teach it to ask. The philosophical stakes ripple beyond geology. If AI becomes the primary lens through which we view cosmic history, what might we overlook? Ancient impact craters aren't just scientific data. They're time capsules holding clues about Earth's climate, the evolution of life, even the distribution of precious metals. When an algorithm classifies a crater as high probability based on statistical similarity, it risks flattening these multidimensional stories into binary outputs. Some researchers propose a middle path, using AI as a scout to flag anomalies, then deploying human expertise to interpret them. It's a partnership playing out in places like Arizona's Meteor Crater, where machine learning guides drills to promising sampling sites, but geologists hand analyze the extracted cores for microscopic evidence of shock metamorphism. Perhaps the most profound implication lies in how AI reshapes our relationship with deep time. These algorithms process millennia of planetary history in minutes, compressing epochs into datasets. There's a strange poetry in that machines built by the youngest species on Earth unraveling the oldest scars in the solar system. As we delegate more of this detective work to silicon minds, we're forced to confront what it means to discover. Is finding a crater just about locating a depression on a map, or is it about reconstructing the moment, billions of years ago, when the universe reached out and touched our world? The answer might determine whether AI becomes merely a tool or the author of the next chapter in Earth's cosmic biography. Earth's surface is like a book with pages glued together. each layer a chapter written in stone, violence, and time. Nested craters are its most dramatic passages, where one cataclysm etches over another, leaving a palimpsest of cosmic collisions. Peel back the Chicxulub crater, and you might find an older impact beneath it, like finding an ancient manuscript hidden under a medieval painting. This isn't just geology, it's planetary archaeology, where every crater is a ruin and every layer a clue to a forgotten disaster. Human cities echo this same pattern. Walk through Rome, and beneath your feet lie layers of history, Renaissance palazzos atop medieval streets, which themselves sit on Roman forums built over Etruscan graves. The difference: Earth's layers span millions of years, not centuries. The Sudbury Basin's nickel deposits aren't just ore. They're relics of a 2-billion-year-old impact that rearranged the planet's crust, trapping metals like artifacts in a buried city. Even our language reflects this kinship. Geologists speak of crater rims and impact basins, terms that could just as easily describe the walls of Troy or the moats of ancient Babylon. But Earth isn't unique in this layered storytelling. The Moon's Mare Imbrium, a vast lava plain, hides ghost craters, faint circles barely visible under younger volcanic flows. Mars' Jezero crater, now explored by the Perseverance rover, shows sediments deposited long after the initial impact, like a desert reclaiming a battlefield. These worlds remind us that planets don't erase their pasts, they bury them, waiting for someone to dig. The cosmic perspective shifts everything. If nested craters are universal, then violence isn't an anomaly, it's the norm. Our solar system is a shooting gallery where worlds trade scars like stories. Jupiter's moon Callisto wears its craters like tree rings, each a timestamp of bombardment. Mercury's Caloris Basin, one of the largest impacts in the solar system, has smaller craters peppered inside it, a celestial Matryoshka doll. Even asteroids, those tiny wanderers, bear layered scars from collisions older than Earth itself. What emerges isn't just a history of destruction, but resilience. Every crater, whether on Earth or Mars, is a testament to survival, our planet's ability to absorb chaos and keep spinning. The layers aren't just rubble, they're records of endurance written in fire and stone, and as we learn to read them, we're not just uncovering the past. We're preparing for the future, one impact at a time. The Moon's surface tells a story Earth can't, a pristine record of cosmic violence, untouched by wind or water. Unlike our planet, where erosion and tectonics constantly rewrite the surface, the Moon's craters remain frozen in time, their nested layers perfectly preserved. Take the magnificent Oriental Basin, a 500-mile-wide bullseye near the Moon's western edge. Its 3 concentric rings, formed by an ancient impact so powerful it sent shockwaves through the entire lunar crust, are so clear they might as well have been etched yesterday. But peer closer at NASA, high-resolution images, and something even more fascinating emerges. Smaller, older craters tucked between the rings, like footprints on top of footprints. These ghost craters, partially buried by lava flows from later volcanic activity, reveal a timeline of bombardment, showing how the Moon endured wave after wave of asteroids long before its volcanic fires cooled. Mars, though scarred by thin winds and ancient floods, offers its own version of this layered history. The Hellas Basin, an 8-mile deep impact crater nearly the size of Australia, holds a secret in its chaotic floor. Satellite scans reveal strange, circular depressions within the basin, likely remnants of older impacts that were shattered but not erased when Hellas formed. Even more telling are the pasted-on-terrain features near Mars' poles, where radar has detected what might be nested craters buried under layers of ice and dust. These hidden structures, invisible to the naked eye, suggest that Mars, like Earth, has been struck repeatedly in the same locations over billions of years. Then there's Mercury, the solar system's battered punching bag. With no atmosphere to soften blows, its surface is a museum of overlapping cataclysms. The Caloris Basin, Mercury's largest impact feature, stretches 900 miles wide and is ringed by concentric fractures. But inside this colossal scar, NASA, a messenger spacecraft, spotted something unexpected: dozens of smaller craters with unusual, wrinkled floors. These aren't random later impacts, they're floor-fractured craters. They're strange textures hinting at volcanic activity triggered by the original collision. It's as if Mercury's crust, shattered by the Caloris impact, became a canvas for secondary disasters, where lava seeped through cracks to reshape older wounds. What makes these off-world craters so valuable is their clarity. Without Earth's dynamic geology to erase the evidence, they preserve a textbook of impact physics. The Moon's ghost craters teach us how lava can bury but not destroy. Mars' hidden rings show how even mega impacts can't fully overwrite past collisions. Mercury's fractured floors reveal how impacts can ignite volcanic chains, turning one catastrophe into many. These lessons are priceless for decoding Earth's obscured history. When we find a crater like Sudbury or Chicxulub with strange mineral layers or gravity anomalies, we can now ask, is this a Mercury-style fracture zone? A lunar ghost peeking through, the solar system becomes our Rosetta Stone, helping translate Earth's cryptic scars. Yet for all these parallels, Earth stands apart. Our planet's craters aren't just relics, they're alive, reshaped by oceans, forests, and the slow dance of continents. Where the Moon's Tycho crater sits unchanged for 1 billion years, Earth's Redifort has been folded and twisted by tectonic forces until only its bones remain. This dynamism makes Earth's impact record harder to read, but also richer. Each buried crater isn't just a wound, it's a seed, influencing everything from ore deposits to ecosystems. The cosmos may have written the same violent story across every rocky world, but only Earth has rewritten its ending, turning catastrophe into the cradle of life. Earth's surface is the ultimate disappearing act, a stage where cosmic collisions leave their mark, only to be erased by the planet's relentless restlessness. Unlike Mars or the Moon, where craters sit untouched for billions of years like museum exhibits, Earth's crust is a dynamic canvas, constantly repainted by plate tectonics, weathered by wind and water, and recycled through volcanic fires. Take the Redifort crater in South Africa, once a gaping wound 200 miles wide. 2 billion years of tectonic shifts have folded and twisted its structure until only a ghostly ring of hills remains, a whisper of the asteroid's fury. Compare that to Mars' Hellas Basin, a crater nearly the same age and size, where the stark, uneroded rim still towers over the landscape like a monument to violence frozen in time. This geological amnesia isn't just a quirk. It's a puzzle with high stakes. Every crater lost to erosion or buried under sediment is a missing page in Earth's autobiography. When researchers drilled into the Chesapeake Bay impact structure, they found a jumble of shattered rock and melted minerals, but the crater's original shape had been smeared by millennia of sediment, like a fingerprint rubbed away. Contrast that with Mercury's Caloris Basin, where the impact's concentric rings remain crisp as the day they formed, untouched by atmosphere or ocean. Earth's craters don't just fade, they're actively dismantled, their evidence scattered like clues in a cold case. Yet this elusiveness is precisely what makes every discovery revolutionary. Finding a hidden crater on Earth isn't just about adding another pin to the map. It's about rescuing a story from oblivion. When scientists confirmed the Hiawatha, a crater under Greenland's ice in 2018, it wasn't just the size that stunned them. it was the fact that it survived at all. Most craters that Young estimated at 12,000 years would have been ground to dust by glaciers. Hiawatha has preservation under ice was a fluke, a cosmic message in a bottle washed ashore by luck. Each of these rare finds forces us to rewrite history. The Deniliquin crater in Australia, potentially the largest ever at over 300 miles wide, could rewrite our understanding of the Ordovician extinction, if only erosion hadn't chewed away the smoking gun. This dance between destruction and discovery taps into something primal in the human psyche. We're drawn to cataclysms not just for their spectacle, but for their power to reset the narrative. Ancient myths from every culture speak of world-ending fires and floods, echoing real events like the Younger Dryas impact hypothesis, a controversial theory that a comet strike 13,000 years ago triggered an ice age. Modern cinema obsesses over asteroid disaster films, while scientists meticulously track near-Earth objects. Perhaps it's because deep down we recognize that Earth's scarred surface isn't just a record of past violence, it's a preview. Every crater we uncover, no matter how fragmented, is a reminder that our planet's story is still being written, one impact at a time. In the end, Earth's rarity isn't just a scientific challenge, it's a narrative one. Mars and the Moon offer clarity, but Earth offers mystery. Their craters are static, frozen in time. Ours are fleeting, layered with meaning, and all the more precious for their impermanence. The next time you walk across a field or hike a mountain ridge, consider this. Beneath your feet, the ground might still remember the day the sky fell. You just have to know how to listen. There's something primal about standing at the edge of a massive crater, staring into the abyss where the sky once fell. It's not just the scale that unnerves us, it's the randomness, the reminder that catastrophe can strike without warning, rewriting history in an instant. Nested craters amplify this unease. They're not singular tragedies but layered disasters, proof that cosmic violence isn't a one-time event but a recurring nightmare. This taps into our deepest fears, the idea that survival isn't guaranteed, that progress can be undone by forces beyond our control. It's no coincidence that cultures across time have woven doomsday myths around falling stars and fiery skies. These stories are echoes of real events, passed down through generations like geological strata of collective memory. Pop culture thrives on this fascination. Blockbusters like Deep Impact and Armageddon don't just entertain, they let us rehearse the unthinkable, transforming abstract fears into narratives with heroes and resolutions. The Don't Look Up satire, with its scathing take on humanity's denial of impending disaster, resonates because it mirrors our real-world ambivalence toward cosmic threats. Even video games like The Outer Wilds, where players uncover the ruins of a civilization wiped out by a supernova, tap into the haunting allure of cataclysm. These stories aren't just escapism, they're coping mechanisms, helping us process the existential dread that nested craters embody, the possibility that extinction isn't an if but a when. Yet science offers a counterbalance to this fear. Every crater we map, every layer we decode turns chaos into comprehension. The discovery that Chicxulub might hide an older impact isn't just a geological footnote, it's a revelation that reshapes how we perceive risk. By studying these nested scars, we're not just charting the past, we're rehearsing for the future. Programs like NAS, a Planetary Defense Coordination Office, which tracks near-Earth objects, aren't born from paranoia, but from the hard-won knowledge that understanding Earth's impact history is the first step toward altering its next chapter. When the DART mission successfully nudged an asteroid off course in 2022, it wasn't just a technological triumph, it was proof that fear, when channeled into curiosity, can become our greatest defense. This shift from dread to preparedness mirrors humanity's broader relationship with disaster. Just as early humans turned lightning strikes into myths before unraveling the science of electricity, we're now transforming cosmic threats from omens into equations. The same tools that uncover buried craters, LiDAR, AI, seismic surveys, are also refining our ability to predict and deflect future impacts. It's a poignant cycle. The scars that once symbolized our vulnerability are now the blueprints for our resilience. So the next time you see a headline about a city-killer asteroid whizzing past Earth, remember, those nested craters aren't just relics of doom. They're guideposts showing us how to navigate a universe that's as unpredictable as it is beautiful. And in that balance between awe and action, we find not just survival, but the chance to write a better ending. Earth's hidden craters aren't just relics of the past, they're training grounds for planetary survival. Every buried impact zone, every layered catastrophe we uncover, sharpens our ability to anticipate and deflect the next cosmic threat. Take NASA's DART mission, humanity's first real-world test of asteroid deflection. In 2022, this refrigerator-sized spacecraft slammed into a small moonlet named Dimorphos, altering its orbit around a larger asteroid. The mission's success wasn't just luck, it was built on centuries of studying Earth's own collision history. By analyzing ancient craters like Chicxulub, scientists calculated the energy needed to nudge an asteroid off course, proving that understanding old wounds can teach us how to prevent new ones. But deflection is only half the battle. The real challenge lies in spotting incoming threats early enough to act. That's where initiatives like the Pan-STARRS telescope in Hawaii come in, scanning the skies nightly for faint, fast-moving dots that could signal trouble. Since its launch in 2010, Pan-STARRS has discovered over half of all known near-Earth objects, including the infamous Oumuamua, our first recorded interstellar visitor. Yet even this high-tech sentinel has blind spots. Asteroids approaching from the direction of the Sun, like the 20-meter Chelyabinsk meteor that exploded over Russia in 2013, remain virtually invisible until it's too late. This is where Earth's hidden craters offer crucial intelligence. By mapping ancient impact patterns, researchers have identified risk corridors, regions of space where asteroids are statistically more likely to originate. It's cosmic epidemiology, tracing the paths of past disasters to predict future outbreaks. The Catalina Sky Survey in Arizona takes this a step further, using machine learning to sift through terabytes of telescopic data for telltale signs of movement. In 2020 alone, it spotted over 1,200 new near-Earth objects, some as small as a school bus. But size can be deceiving. The Barringer crater in Arizona, barely a kilometer wide, was carved by an iron meteorite no larger than a house, proof that even modest space rocks can leave devastating scars when traveling at 40,000 miles per hour. What makes these efforts so urgent isn't just the threat we know, it's the ones we don't. Earth's hidden craters reveal a disturbing pattern. Impacts often come in clusters. The Ordovician extinction 450 million years ago coincided with multiple asteroid strikes, while the late heavy bombardment reshaped the entire inner solar system. Today's detection networks, for all their sophistication, might miss a similar swarm. That's why the European Space Agency's Fly-Eye telescope, set to begin operations in 2024, uses a radical new design inspired by insect eyes. Its 16 separate cameras will scan wide swaths of sky simultaneously, increasing the odds of catching stealthy asteroids that slip through conventional surveys. Yet technology alone isn't enough. The most powerful tool in planetary defense might be curiosity itself. When amateur astronomer Gennady Borisov spotted an odd, fuzzy object in the Crimea in 2019, It turned out to be the second known interstellar visitor, later named 2I/Borisov. His $10 telescope and sharp eyes proved that discovery isn't just for professionals. Initiatives like NASA's Asteroid Hunters project invite citizen scientists to scour satellite data for undiscovered craters, turning planetary defense into a global mission. The lesson from Earth's hidden craters is clear. Cosmic violence isn't a question of if, but when. Whether it's dart-defiant shove against dimorphos or a teenager spotting a strange dot in a telescope, every action we take writes a new chapter in an old story, one where humanity evolves from passive victim to active guardian. The craters beneath our feet aren't just scars, they're roadmaps showing us how to navigate a future where the sky doesn't fall. You don't need a PhD or $1 million lab to uncover Earth's cosmic scars sometimes. All it takes is a curious mind and a laptop. In 2013, an Italian amateur geologist named Vincenzo de Michele was scrolling through Google Earth when he noticed something odd in the Egyptian desert. A near-perfect circular depression half a mile wide, surrounded by smaller divots. Using free satellite tools and topographic maps, he cross-referenced the site with geological surveys, eventually convincing professionals to investigate. The result, the Camel Crater, a pristine impact site so young estimates suggest 5,000 years, that its metallic meteorite fragments still litter the sand. De Michele's discovery wasn't a fluke. From Australian farmers recognizing strange, glassy rocks as impact debris to a British schoolteacher identifying a potential crater under the North Sea, everyday explorers are rewriting the map of Earth's violent past. So how can you spot these hidden scars? Start by training your eye on circular landforms, but don't be fooled by lookalikes. Volcanic calderas often mimic craters, but they're usually more irregular and surrounded by lava flows. Erosion can carve bowl-shaped valleys, but these lack the telltale signs of cosmic collisions, raised rims, central uplifts, or radial debris patterns. Free tools like NAS, a World Wind, or the USC's Earth Explorer let you overlay geological data, highlighting mineral anomalies like shocked quartz or nickel-rich soils that scream impact. Zoom in on suspicious circles, concentric fractures, magnetic field disruptions, or even unusual vegetation can hint at buried structures. The key is context. When a retired engineer in Sweden noticed a ring of stunted pine trees on satellite images, researchers confirmed it marked the rim of the mean crater, hidden under peat bogs for 100 million years. The real magic happens when amateurs and pros team up. Online hubs like the Cosmic Research Group or Reddit's r/impact craters buzz with activity, where hobbyists post coordinates and experts weigh in with ground truthing. In 2020, a thread on the Cloudy Nights Astronomy Forum led to the rediscovery of a forgotten crater in Argentina, after a user cross-referenced 19th century survey notes with modern elevation data. Universities are getting in on the action too. The University of New Brunswick's Crater Hunter project crowdsources analyses of satellite imagery, with volunteers earning co-authorship on papers for verified finds. Even gaming tech plays a role. The same algorithms that generate realistic terrain in titles like Microsoft Flight Simulator are now being adapted to simulate erosion patterns, helping distinguish natural basins from impact relics. What makes this grassroots movement so powerful isn't just the extra eyes, it's the fresh perspectives. Professionals might focus on textbook criteria, but amateurs often notice oddities that defy expectations. When a German baker with a passion for topography spotted a peculiar horseshoe-shaped ridge in the Bavarian Alps, experts initially dismissed it as glacial. His persistence paid off. Drilling revealed it was the eroded remnant of a 24-million-year-old crater, its original circular shape warped by tectonic shifts. Stories like these prove that crater hunting isn't just for scientists, it's a living history lesson, one where anyone with curiosity can contribute to uncovering Earth's untold stories of fire and rebirth. As we stand on the brink of countless undiscovered impacts, the invitation is open. The next great crater might be hiding in plain sight, waiting for someone, maybe you, to connect the dots between a strange landform and the cosmos' fingerprints. And when that happens, it won't just be a personal triumph. It'll be another piece of the puzzle, revealing how our planet's past shapes its future. Beneath the emerald canopy of the Amazon rainforest, where rivers snake through untouched wilderness, satellites have detected a peculiar gravitational dip, a circular anomaly spanning nearly 20 miles. Scientists suspect this could be the ghost of an ancient impact, its crater long buried under layers of sediment and dense vegetation. Similar whispers echo from Siberia's frozen tundra, where ground-penetrating radar has mapped concentric fractures beneath the permafrost, hinting at a colossal strike older than the ice itself. These are the frontier zones of crater science, places where Earth's next great secret might be hiding, waiting to rewrite our understanding of cosmic collisions. One of the most tantalizing puzzles lies beneath the North Sea's churning waves, the Silver Pit structure, discovered in 2002 by oil geologists reviewing seismic data. This nested ring of fractures resembles a bullseye etched into the seabed. Some argue it's the remnant of a 200-million-year-old impact, its layers distorted by tectonic shifts. Others contend it's a salt dome collapse, a natural phenomenon with uncanny mimicry. The debate rages because Silver Pit's truth could reveal whether Earth's oceans conceal a graveyard of unseen craters, their stories dissolved by time and tides. Then there's Australia's Gawler Ranges, where magnetic surveys have uncovered a sprawling, 300-mile-wide disturbance in the crust. Mineral samples show telltale signs of extreme pressure, yet no surface scar remains. Could this be the eroded root of a nested impact, its original rim vanished under eons of wind and dust? Or consider the Bangui magnetic anomaly in Central Africa, a massive underground zone where Earth's magnetic field spikes unnaturally. Some researchers speculate it's the iron-rich heart of a buried asteroid, slowly rusting beneath the jungle, a relic from a time when the sky rained fire. What makes these hunts so electrifying isn't just the potential discoveries, it's the tools revolutionizing the search. Hyperspectral imaging now scans entire continents for mineral fingerprints like shocked quartz, while quantum gravity sensors detect density variations deeper than ever before. In Brazil's Parnaíba Basin, these technologies have flagged a 50-mile-wide subterranean dome, its rock layers jumbled as if stirred by a giant's hand. Drilling campaigns there could soon confirm whether it's Earth's next confirmed megacrater, yet for all our technology, serendipity still plays a role. The Deniliquin structure in Australia, potentially the largest impact zone on Earth, was first noticed by a farmer spotting odd, glassy stones in his sheep pasture. Similarly, the Hiawatha crater in Greenland remained hidden under ice until a glaciologist noticed an eerie, bowl-shaped depression in radar maps, a reminder that some of Earth's greatest secrets are still tucked in plain sight. Every uncharted crater is more than a geological curiosity. It's a missing page in Earth's survival guide, a lesson in resilience written in shattered rock. As explorers probe these last frontiers, from the Amazon's hidden basins to Antarctica's icy depths, they're not just chasing scars. They're uncovering the invisible threads that weave our planet's violent past into its fragile present. And with each discovery, we're reminded Earth's story isn't locked in stone. It's still being written one impact at a time. Drilling into an ancient impact crater isn't just a scientific endeavor, it's a moral crossroads. These cosmic scars are more than geological formations. They're time capsules preserving snapshots of Earth's most violent moments. When researchers propose extracting core samples or mining for minerals, they're faced with an impossible choice: unravel the crater's secrets or leave it untouched as a natural monument to planetary history. The Sudbury Basin exemplifies this tension. Its nickel deposits fuel industries worldwide, but every ton of ore hauled from the ground erases layers of evidence about the asteroid impact that created it 2 billion years ago. Mining companies now work alongside geologists to document shock-metamorphosed rocks before they're smelted away, a fragile compromise between exploitation and preservation. This dilemma mirrors controversies in other frontier sciences. Antarctic ice cores, like those from Lake Vostok, contain climate records stretching back 800,000 years. Drilling risks contaminating these pristine archives with modern microbes, yet without penetrating the ice, we'd never have discovered ancient atmospheric CO2 levels or prehistoric viruses. Similarly, hydrothermal vents on the ocean floor teem with undiscovered life forms, but mining companies eye their mineral-rich chimneys. The International Seabed Authority struggles to balance bioprospecting with conservation, much like crater researchers weighing knowledge against preservation. The stakes escalate with rare, well-preserved craters. The Hiawatha crater under Greenland's ice is a Rosetta Stone for understanding young impacts. Its pristine state offers clues about how asteroids interact with ice sheets, critical data for predicting sea level rise from future strikes. But drilling through its icy shield risks introducing modern contaminants that could skew climate records. Some argue such sites should be designated UNESCO World Heritage status, protected like Cambodia's Angkor Wat or Australia's Great Barrier Reef, not as cultural treasures but as planetary ones. International collaboration offers a path forward. The Chicxulub scientific drilling project brought together 30 nations to extract cores without collapsing the crater's delicate structure. Their findings rewrote our understanding of mass extinctions, proving cooperation can yield breakthroughs while minimizing harm. Similar models now guide exploration at South Africa's Redifort Dome, where ecotourism helps fund conservation. Visitors walk trails lined with impact brexias, their ticket dollars preserving the very rocks they come to see. Perhaps the answer lies in seeing craters not as resources to exploit or relics to lock away, but as classrooms. The Rise crater in Germany doubles as both a research site and an open-air museum, where schoolchildren hold shatter cones formed during impact. In Canada's Mistyston Lake, indigenous communities collaborate with scientists, blending traditional knowledge with cutting-edge geology to tell the crater's full story. These partnerships recognize that craters belong to humanity's shared heritage, not just as scientific datasets, but as monuments to our planet's resilience. As we stand on the brink of discovering more hidden impacts, the choices we make today will echo through generations. Will we treat these cosmic wounds as quarries, stripping them for short-term gain, or safeguard them as archives, ensuring future scientists armed with better tools can decode stories we can't yet imagine? The middle path demands creativity, drilling selectively, mining responsibly, and always remembering that these scars aren't just scars. They're the fingerprints of the universe itself, pressed into the skin of our world. Earth's surface isn't just a landscape, it's a living archive where every hidden crater tells a story of chaos and rebirth. These cosmic scars aren't merely wounds, they're time capsules, preserving snapshots of moments when the universe reached out and reshaped our planet. From the layered secrets beneath Chicxulub to the mineral-rich depths of Sudbury, each impact zone is a puzzle piece in Earth's turbulent history. They hold clues to ancient climate disasters, mass extinctions, and even the origins of life itself. But what makes them truly extraordinary isn't just their scientific value, it's how they bridge the gap between geology and humanity, connecting raw cosmic violence to the cultural myths and survival stories passed down through generations. The tools we use to uncover these secrets are just as remarkable as the discoveries themselves. LiDAR strips away forests to reveal buried bullseyes, while AI sifts through satellite data like a digital detective, spotting patterns invisible to the human eye. Ground-penetrating radar acts as a geological X-ray, and seismic surveys listen to echoes of impacts that happened millions of years ago. Yet for all this technology, some of the most thrilling breakthroughs still come from human curiosity. A farmer noticing strange rocks, an amateur astronomer spotting an anomaly on Google Earth. It's a reminder that science isn't just about machines, it's about the relentless drive to explore, to question, and to piece together the fragments of our planet's past. But these craters aren't just relics, they're warnings. Every nested impact, every layered catastrophe we uncover, teaches us that cosmic violence isn't a one-time event. It's a rhythm, a pattern woven into Earth's history. The same forces that sculpted our planet still lurk in the cosmos, and understanding them isn't just academic. It's survival. Programs like NASA's DART mission prove we're no longer passive victims of the universe's whims. We're becoming guardians, using the lessons of ancient craters to deflect future threats. Yet beneath all the science and technology lies something deeper, a humbling connection to the cosmos. Those craters, whether hidden under ice or buried beneath cities, remind us that Earth isn't an isolated haven. It's a participant in a vast, dynamic solar system where collisions and rebirths are part of an endless cycle. The minerals we mine from impact sites, the climate models we refine from their debris, even the myths they inspired, all of it ties us to something grander. So the next time you walk across a field or gaze at a mountain range, remember, the ground beneath your feet might be hiding a secret, a crater within a crater, a story within a story. And as we keep searching, drilling, and decoding, we're not just uncovering Earth's past, we're learning how to safeguard its future, one cosmic clue at a time. We stand on the skin of a planet etched with invisible stories, each crater a whisper from the cosmos, reminding us how small we are in the vast theater of time. These scars, some hidden for eons beneath forests and cities, others worn smooth by millennia of wind and rain, are more than just geological oddities. They're portals to moments when the universe reached out and touched our world with unimaginable force, reshaping continents, extinguishing species, and yet, against all odds, leaving the door open for life to begin again. Carl Sagan once said, "The cosmos is within us, we are made of star stuff." And nowhere is that truth more palpable than in these impact zones, where the debris of asteroids mingles with the very rocks beneath our feet, where the iron in our blood shares lineage with the dust of distant supernova. But these craters are also mirrors. They reflect not just Earth's violent past, but our own restless curiosity. Every time a scientist peers into a core sample, every time an amateur spots a suspicious circular ridge on a satellite map, we're proving that humanity's greatest strength isn't just survival, it's wonder. The same cosmic chaos that carved these scars also forged the elements that built our civilizations, the water that fills our oceans, even the carbon in our bones. We are, in every sense, children of the cosmos, born from its violence and cradled by its improbability. So look up, not just at the stars, but at the ground beneath you. The next time you walk through a field or hike a mountain trail, remember, you might be tracing the rim of a crater you can't even see, stepping over the echoes of an explosion older than trees, older than dinosaurs, older than continents. And when you tilt your head back to the night sky, know that the same forces that shaped our planet are still out there, weaving new stories in the darkness. If this journey through Earth's hidden scars has sparked your curiosity, share your thoughts below. Have you ever stumbled upon a landscape that made you wonder about its cosmic secrets? Hit subscribe to join us as we keep unraveling the mysteries buried beneath our feet, because the next great discovery might just be waiting for someone like you to uncover it. Until then, keep looking up and down. The universe has left its fingerprints everywhere. All we have to do is learn